ANM, American Northwest Magazine. Please subscribe.
You know, we hear the words AI revolution everywhere, but the real story, the big story, isn't just about the famous chips everyone's talking about. It's about this entire hidden ecosystem, this incredible machinery that makes it all work. And today, we're going to pull back that curtain. So let's just be honest for a second. When you think AI stocks, what's the first name that pops into your head? It's Nvidia, right? Of course it is. They've absolutely dominated the conversation, and for very good reason. But here's the thing. Focusing only on them is like staring at the very tip of a colossal iceberg. Because the truth is, this AI boom is a massive interconnected ecosystem. Think of it like a stack of technologies, where every single layer is absolutely critical. So today, we're going to dive deep. We're going to explore those hidden layers and meet some of the unsung heroes who are really powering this whole revolution. So here's our game plan. First, we're going to look beyond the GPU gold rush. Then we'll dig right down to the foundation, how silicon is actually forged. After that, we'll move up to the massive infrastructure needed to power it all, see how AI gets put to work, and then we'll zoom way out to the global game board of what's called sovereign AI. All right, let's jump in. Section 1. Beyond the GPU gold rush. Before we can find where the hidden opportunities are, we got to understand why everyone is digging in the exact same spot. And, more importantly, why the really smart money is starting to look somewhere else entirely. Look, Nvidia's success is it's undeniable. But with a market cap soaring into the trillions, you have to realize a lot of that future growth is already baked into the price. But that's not the end of the story. No way. It's the beginning. It forces us to ask a better question. Where's the next big wave of growth coming from? And the answer, well, it lies much deeper in the supply chain. So let's go there. Let's go right to the very, very bottom of the AI stack. We're talking about the almost magical, mind-bogglingly microscopic machinery that actually forges the silicon brains of AI. You should think of these companies as the ones selling the picks and shovels in this digital gold rush. First up, ASML. These guys have a complete monopoly on what are called EUV machines. They're literally the only tools on Earth that can print the most advanced AI chips. Then you've got Lam Research. Their tools are the master etchers, carving these impossibly tiny pathways that high-speed memory needs to function. Applied Materials is kind of the jack of all trades, supplying tools for the entire process. And KLA Corp, they're the perfectionists, the quality control making sure every single chip is flawless. And this quote right here, it just says everything. ASML isn't just another supplier. It is a fundamental technological choke point, period. Without their machines, the world's most advanced AI processors simply do not get made. It makes these foundational companies utterly and completely indispensable. Okay, so we've got the microscopic chips. Fantastic. But where do they live? This is where we move up the stack to the enormous physical world that has to be built just to support them. We're talking about power and pipes. Just get a load of these numbers. This isn't a small upgrade we're talking about here. A single AI rack can demand 10 times the power of a standard one. That is a monumental leap, and it creates a colossal engineering problem: heat. All of that power, all that energy, it turns these servers into furnaces that somehow have to be tamed. And how are the big guys solving this? Well, with an unbelievable fire hose of cash. The big tech hyperscalers, we're talking Microsoft, Amazon, Google, Meta, they're on track to spend over $700 billion in a single year just to build out this infrastructure. That is a staggering amount of money, and it all has to go somewhere. And this is where a lot of it is going. You see that massive heat problem we just talked about? Well, companies like Vertiv are right there to solve it with super specialized liquid cooling systems. And the challenge of getting thousands of GPUs to talk to each other like one giant brain? That's where Arista Networks comes in with their insane, high-speed networking gear. These companies are standing right in the path of that $700 billion fire hose. Okay, so we've forged the silicon, we've built the data centers, but all that hardware, it's just potential. It's just sitting there. So how does all this raw power get translated into actual intelligence that a business can use? For that, we have to move up to the software layer. Now, this is a really crucial distinction to get. On one hand, you have horizontal AI. These are broad tools that help with general stuff, like summarizing a document. But then you have vertical AI, and this is the deep stuff. This AI is built on proprietary, industry-specific data to solve very specific, high-stakes problems, like forecasting demand for an entire retail chain. And because it's so specialized, its competitive moat, its ability to defend itself is just so much stronger. And this, right here, is the key. Vertical AI isn't some feature you just turn on and off. It gets woven into the very fabric of a company's day-to-day operations. It's not an add-on. It becomes the core engine. And that deep, deep integration makes it incredibly sticky and basically indispensable. And just look at how fast this is all moving. We went from simple, rules-based systems to machine learning that could actually predict the future. Now, with generative AI, we can literally talk to complex data using plain English. And the next step? We're looking at fully autonomous systems that can run entire workflows with very little human oversight. The pace is just incredible. So we've covered the corporate and the technological layers, but when a technology gets this powerful, this integrated into everything we do, it stops being just about business. It becomes a matter of national interest, of national security. So for our final layer, let's zoom all the way out to the global game board of sovereign AI. So what exactly is sovereign AI? Well, to put it simply, it's a nation's ability to build and control its own AI destiny. It's about maintaining independence over your data, your technology, and the laws that govern it all. Really, it's about achieving digital autonomy in a world completely driven by AI. But achieving this sovereignty, it's not simple. It forces nations to ask 4 really tough questions. First, territorial. Are our servers and our data physically on our own soil? Second, operational. Do we hold the keys to our data centers? Third, technological. Are we just renting this tech from someone else, or do we actually own the intellectual property? And finally, legal. At the end of the day, whose laws govern our digital world? And make no mistake, people are taking this incredibly seriously. A recent McKinsey survey found that a whopping 71% of global leaders see sovereign AI as either a strategic imperative or an existential concern. This has rocketed from a niche policy discussion to a central issue of national competitiveness and security. So there you have it. We've gone from the microscopic picks and shovels forging silicon at the very foundation, all the way up to the massive data centers with their power and pipes, through the intelligent software applications that make it all useful, and finally to the high-stakes geopolitical game board of sovereign AI. That is the complete AI stack. Which really leaves us with one final crucial question to chew on. As this incredible technology gets more and more embedded in our companies, in our countries, and in our own daily lives, how much of the intelligence that we all come to rely on will we or our nations truly own?
Whenever there's a really massive gold rush, everyone just fixates on the prospectors.
Right, yeah, the
Yeah.
guys out in the mud.
Exactly. The people out there panning for gold, just hoping to strike it rich overnight.
Yeah.
But, history tells us a very different story about where the actual wealth was consolidated.
Oh, absolutely.
The surest way to make an absolute fortune during a gold rush wasn't finding the gold, it was being the person selling the picks and the shovels.
It totally comes down to owning the infrastructure. The foundational tools that make the extraction or, well, in the modern context, the computation even mathematically possible.
Right. And right now we are sitting right in the middle of arguably the biggest technological gold rush in human history. With this artificial intelligence boom.
Without it.
Everyone is talking about the new AI models, the generative software, the tech giants battling it out. But for this deep dive, we are pulling back the curtain. Looking at our materials for today, specifically these fantastic financial notes and market data titled AI Investment Infrastructure, the Semiconductor Supercycle from April 2026. So the mission for you, the listener, is to understand this massive, completely hidden backbone.
The physical reality of it all.
Yes. We're looking closely at the specialized companies that build these multi-million-dollar machines required to manufacture high-end chips. I mean, these are the ultimate modern-day picks and shovels.
They really are. And, the physical reality of AI is almost entirely invisible to the average consumer. We interact with software, we query complex models on our phones, but
It lives somewhere physical.
exactly. That software demands a level of physical manufacturing precision that it pushes the absolute outer boundaries of physics, optics, material science, all of it.
So let's start with the absolute bottleneck of this entire industry, because if AI is a gold rush, there is one company that essentially holds a total undisputed monopoly on the only shovels capable of digging for the highest grade gold.
The big one.
Yeah, we have to start with the Dutch multinational, ASML.
I mean, if you are analyzing the global semiconductor supply chain, ASML is the most critical single point of failure on the entire board.
The 2026 market data highlights their extreme ultraviolet lithography machines, EUV.
Right.
These are the tools that basically print the microscopic circuits for the most advanced 2-nanometer and 3-nanometer chips. And when I was looking through these notes earlier, I was really trying to wrap my head around that kind of scale.
It's hard to conceptualize.
It really is. I mean, printing a 2-nanometer chip is basically like trying to draw a wildly detailed map of the entire world, mapping out every single street, alleyway, and building on a single grain of sand.
That is a phenomenal way to visualize that spatial constraint. And ASML as well, they're the sole manufacturer of the only pen capable of drawing that microscopic map.
But these pens carry an unbelievable price tag. We're talking about machines that cost, what, between $350 million and $400 million each. And looking at their April 2026 outlook, ASML raised its revenue projection to between 36 billion and 40 billion euros.
Yeah, the numbers are just staggering.
And the notes attribute this to the industry's massive shift toward AI inference and the rollout of something called high-NA EUV. Before we go further, what exactly is the shift to AI inference, and what does high-NA even mean?
Sure. So AI inference is what happens after an AI model is already trained.
Okay.
Training is teaching the brain, right? But inference is the brain actually answering your questions in real time.
Oh, got it.
And as AI gets embedded into literally every device, the volume of inference processing is exploding. That demands incredibly power-efficient, highly advanced chips. To make those, ASML is rolling out high-NA, or high numerical aperture, EUV.
Which does what exactly?
Well, without getting bogged down in an optics textbook, high-NA essentially uses significantly larger, much more advanced mirrors. This allows the light to strike the silicon at a wider angle.
Okay.
And that wider angle is exactly what lets them print even thinner, tighter lines than standard EUV.
Okay, but here is where I have to push back a little on the market dynamics. I'm looking at these numbers and the sheer dependence the tech world has on this one single company.
That's a lot of eggs in one basket.
It really is. If a single machine costs $400 million and it's this vital to the future of technology, why hasn't a massive tech giant like Apple or Nvidia just copied it?
Right.
Or built their own version? I mean, they have hundreds of billions of dollars in cash just sitting there. Surely an army of well-funded engineers could figure it out.
It's totally the most logical question an analyst could ask.
Yeah.
But it fundamentally misunderstands the mechanism of ASML's moat.
How so?
You just cannot reverse engineer an EUV machine with a big budget because the physics involved literally sound like science fiction.
I'm listening.
To generate extreme ultraviolet light, you can't just, flip a switch. The machine has to shoot microscopic droplets of molten tin through a perfect vacuum.
Wait, molten tin?
Yes. And while that droplet is in midair, a high-power laser shoots it twice.
You're kidding.
No. Once to flatten it into a pancake, and a second time to vaporize it into plasma. And that plasma is what emits the EUV light.
Wait. They're shooting microscopic drops of molten metal out of midair with a laser.
Tens of thousands of times per second.
That is insane.
It gets crazier. Because EUV light is absorbed by literally everything, even air, this entire process must happen in a perfect vacuum.
Oh, wow.
And the light is then directed not by glass lenses, which would just absorb it, but by incredibly precise, perfectly flat mirrors made by a German company called Zeiss.
Okay.
Those mirrors are polished so perfectly that if you blew them up to the size of the Earth, the tallest mountain on them would be a fraction of a millimeter high.
That's just incomprehensible.
Right. So the barrier to entry isn't capital. It's decades of proprietary, localized supply chains and institutional knowledge of manipulating physics at a level literally no one else has achieved.
So bottom line, if you want to build the most advanced AI processors in the world, you have no choice. You pay the toll to ASML.
Precisely. They are the gatekeepers.
All right, so ASML's lasers solve the logic problem. They build the incredibly fast brain of the AI. But making the brain exponentially faster actually creates a massive new problem, right?
It absolutely does.
Because a super fast processor is totally useless if it takes too long to actually retrieve the data it needs to think. The processor just ends up sitting around waiting for data to arrive. So how is the industry solving that data traffic jam?
Well, that data bottleneck is arguably the most critical engineering challenge in the current supercycle. As AI models scale up, traditional memory chips that are just laid out flat on a motherboard, they simply cannot feed data to the logic processor fast enough.
Because of the physical distance?
Exactly. The physical distance the electrical signals have to travel creates latency. So the industry's solution is high bandwidth memory, or HBM.
Which involves stacking memory chips vertically, right? Like instead of a
snap.
sprawling, flat suburb of memory chips where the data has to commute a long way to work, you build a high-density skyscraper of memory sitting directly next door to the processing plant.
Yes, vertical stacking is the key. But to make that memory skyscraper actually functional, the data needs to be able to travel between the floors of that building instantly.
Which brings us to Lam Research Corporation, ticker LRCX. The market notes show they are the leaders in the specialized etching equipment required for this.
They are.
Specifically, they create something called through-silicon vias, or TSVs. To keep our skyscraper analogy going for just a second, Lam Research basically makes the tools that install millions of ultra-high-speed elevator shafts right through the center of the building.
That's exactly what it is.
Right. It lets the data zip straight up and down between the stacked chips instead of taking the stairs around the edges.
Exactly. And the how is just as impressive as ASML's lasers.
Really?
Oh, yeah. You can't use a mechanical drill to create an elevator shaft through an atomic scale silicon wafer. Lam's machines use highly controlled plasma fields, essentially localized electrified gas, to chemically etch or carve these microscopic, perfectly vertical holes straight through the silicon.
Without breaking it.
Right, without damaging any of the surrounding circuitry. Without Lam's etching tools, those incredible chips ASML enables would just be starved of data.
That specific capability really explains the staggering market reaction we're seeing. Our notes show that, driven by the 2026 memory shortage and massive AI server buildouts, Lam Research has seen year-to-date gains exceeding 50%.
It's been a massive run.
But honestly, as a financial analyst looking at that, a 50% leap in just a few months suggests the market is pricing in absolute perfection. I mean, isn't that a massive red flag for overvaluation?
It is a significant risk, yeah. And it's exactly why seasoned investors look for broader stability within the sector. While ASML and Lam Research dominate these specific, highly lucrative choke points,
Like lithography and deep silicon etching.
right, they are still highly sensitive to specific technological shifts. This is where a company like Applied Materials, or AMAT, acts as the massive stabilizing counterweight in the supply chain.
Right, the data specifically frames Applied Materials as the foundational broad base play. But what exactly makes them the foundational concrete compared to the highly specialized tools of Lam or ASML?
So, Applied Materials dominates deposition and materials engineering. Before ASML can print a circuit, and before Lam can etch a trench into it, you have to build the incredibly complex, microscopically thin layers of materials on the bare silicon wafer itself.
Okay.
AMAT builds the machines that lay down these films, insulators, conductors, specialized metals, literally atom by atom.
Atom by atom.
Literally. Because almost every type of chip, from a cutting-edge AI processor down to a basic power regulator for an electric vehicle, requires these deposited layers. AMAT's tools are just ubiquitous.
So they aren't tied to one specific trend.
Exactly. They aren't betting on one specific memory architecture or one node size. Any new semiconductor fab built anywhere in the world requires a massive suite of applied materials equipment just to open its doors.
Wow. So we are layering materials atom by atom. We are vaporizing tin with lasers. We are carving plasma elevator shafts. I mean, when you are operating at this kind of microscopic scale, the margin for physical error must be practically non-existent.
It is absolute zero. When you're manufacturing at the nanometer level, a single speck of dust or an imperceptible vibration in the floor.
It's a vibration.
Yeah, or a temperature fluctuation of a fraction of a degree. Any of that can completely ruin an entire wafer of silicon. And those wafers take months to process and are worth tens of thousands of dollars each.
Which sounds like an absolute nightmare for the foundries. How do you even catch errors on something that small before you've wasted millions of dollars and months of production time?
Well, this is a critical, highly lucrative niche dominated by KLA Corporation, ticker KLAC. They are the undisputed leaders in process control and metrology.
The defect inspectors.
Yes. They build the machines that scan the wafers at various stages of the manufacturing process to find defects that are fundamentally invisible to us. They use a combination of advanced optical scanning and electron beam technology to map the wafer and compare it against the intended design blueprint.
And the market notes highlight that KLA operates with incredibly high profit margins. I suppose that makes sense, right? Because they aren't just selling a piece of hardware, they are selling yield protection.
Exactly.
Like if KLA's machine spots a microscopic flaw early on layer 3, the foundry doesn't waste time and money completing the remaining 70 layers on a doomed chip. They save the foundries billions.
Precisely. There are an essential insurance policy for the foundries. As chips shrink to 2 nanometers and below, the complexity multiplies, which means the likelihood of defects skyrockets. KLA's inspection tools become exponentially more critical, and they naturally command a premium for that necessity.
Okay, let's look at the competitive landscape, because we just mapped out some incredibly lucrative monopolies. ASML, Lam Research, AM Show. Whenever there is a wildly profitable toll booth, someone inevitably tries to build a bypass road. Our notes indicate several international challengers are trying to navigate around these massive moats.
Oh, yeah. The immense cost of this equipment has created a massive financial incentive to find cheaper alternatives.
The notes mention Nikon from Japan as a reliable rival in the older DUV, or deep ultraviolet, segment. But then there is Canon.
Right, Canon.
Canon is attempting to disrupt the market with something called nano-imprint lithography, or NIL. Now, looking at how this works, I have to express some serious skepticism here.
Fair enough.
The notes call it a lower-cost stamping method. We literally just spent 20 minutes talking about $400 million precision lasers, perfect vacuums, and Zeiss mirrors. Now, Canon wants to use a stamping method, like a rubber stamp from a craft store. Can a physical stamp actually compete with an extreme ultraviolet laser?
Your skepticism is entirely justified, and just to be clear, a stamping method will not replace EUV for the ultra-complex, chaotic layouts of an advanced AI logic processor.
Right, that would be crazy.
But what makes Canon's strategy fascinating is that they aren't trying to beat ASML at the bleeding edge of logic chips. They are targeting very specific, highly structured market niches to drastically undercut ASML on cost.
Oh, the data explicitly highlights memory and sensor production for Canon's NIL.
Exactly. Memory chips like the flash storage in your phone and imaging sensors have highly repetitive, uniform, grid-like physical structures.
Okay, I see where this is going.
For those specific applications, if Canon can perfect nano-imprint lithography, which literally involves physically pressing a microscopic template into a specialized resin on the silicon wafer and curing it, they completely bypass the need for massive lasers, perfect vacuums, and specialized mirrors.
Wow.
The equipment is a fraction of the cost, and it uses a fraction of the electricity. It is a highly strategic attempt to carve out a profitable slice of the market where the extreme precision of EUV is simply an unnecessarily expensive overkill.
Use a cheaper tool if it gets the same job done. That makes perfect financial sense for the foundries trying to protect their own margins. Now, the market notes also mention another player, SME, operating out of China.
Yes. SME is a state-backed entity, and according to the notes, they are focused heavily on domestic independence. The data shows they are primarily targeting legacy node DUV equipment, specifically in the 90 nanometer to 28 nanometer range.
So just to clarify, DUV is deep ultraviolet. It is the older 193 nanometer wavelength technology that came before the extreme EUV we talked about with ASML.
Correct.
So SME is decidedly not competing for the cutting-edge AI logic chips right now.
That's right. But looking impartially at the broader market dynamics outlined in our sources, their strategic role isn't to beat ASML at 2 nanometers tomorrow. By mastering these legacy nodes, they are establishing foundational, localized supply chains.
Because older chips are still used everywhere,
Yeah,
right?
exactly. It's crucial to remember that 28 nanometer chips are not obsolete. They are heavily utilized in automotive components, industrial automation, Internet of Things devices, home appliances.
So it's about self-sufficiency.
Yes, mastering that equipment provides a massive degree of domestic self-sufficiency outside of the Western supply chain ecosystem.
Okay, so taking all of this in, we have lasers vaporizing kin, we have plasma etching elevator shafts, we have electron beam defect scanners, and we have international challengers trying to stamp their way in to save money.
It's a lot.
It's a massive ecosystem. So if you are listening to this, trying to understand how a financial analyst actually gains exposure to this entire picks and shovels ecosystem without betting their whole portfolio on one single highly complex machine? How does the market bundle this?
Well, that brings us to strategic investment vehicles, specifically exchange-traded funds or ETFs. The market data highlights two primary funds that institutions and retail investors use to track these infrastructure giants, but they have very different risk profiles.
The first one is the VanEck Semiconductor ETF, ticker SMH. The breakdown here shows it is heavily weighted toward the absolute massive hardware winners.
Very top-heavy.
Yeah, ASML is a top 5 position in this fund, holding about a 5.8% weighting. And it sits right alongside the massive designers and foundries, like Nvidia and TSMC.
Right, SMH is a market cap weighted fund, meaning the biggest companies take up the most space. It is highly concentrated. It basically bundles the prospectors, the companies like Nvidia designing the AI architecture with the foundries digging for the gold, like TSMC.
And the tool makers.
And crucially, the tool makers providing the shovels, like ASML and Lam Research. It is essentially a buy the whole high-end supply chain button.
But that concentration introduces massive risk, right? I mean, if one of those top players falters, the whole fund feels it.
Absolutely.
Which is why the alternative mentioned is the iShares Semiconductor ETF, ticker SOXX. The notes describe SOXX as a broader, modified market cap alternative. It tracks many of the same companies, but it caps the individual weightings.
Right, spreads it out.
Yeah, so a giant like ASML or Nvidia takes up a smaller percentage of the pie compared to SMH, spreading the risk more evenly across the smaller tool makers and material suppliers.
It's just a classic trade-off between capturing concentrated upside during a massive supercycle versus protecting your downside by diversifying across the broader ecosystem.
And speaking of downside, as analysts, we have to look at the pitfalls. Our 2026 outlook paints a picture of a sector in a massive, lucrative, high-growth phase. But it extensively flags two primary risks. First, the geopolitical trade restrictions.
Geopolitics is the ultimate wild card here. The flow of this highly advanced multi-million-dollar equipment is heavily monitored. Semiconductor manufacturing equipment is increasingly viewed by governments as critical national security assets comparable to military hardware.
The export limits.
Precisely. And again, just looking at the market data objectively, we have seen instances where sudden changes in international trade policy can instantly cut off a massive, highly profitable regional market for these equipment manufacturers overnight.
Just with the stroke of a pen.
Yes. The rules of the game can be altered by a single regulatory signature, completely independent of the company's actual technological execution or financial health. It introduces unpredictable structural volatility.
The second major risk flagged in the notes here is the deeply cyclical nature of the semiconductor industry itself. We keep talking about this AI supercycle, but historically, the industry is famous for the bullwhip effect. Massive boom periods followed by crushing overcapacity.
It really is the defining financial characteristic of semiconductor capital equipment. Right now, in April 2026, we are in an incredible infrastructure build-out. Foundries are ordering billions of dollars of equipment, but, trees do not grow to the sky.
Meaning they build way too many factories, demand for the final products normalizes, and suddenly there's a glut of capacity.
Yes. The foundries buy all these incredibly expensive machines from ASML and AMAT. They crank up wafer production to maximum capacity, and if consumer or enterprise demand for the end products cools down even slightly,
They stop buying.
they don't just reduce their equipment orders. They immediately stop them altogether. The equipment manufacturers go from having years-long order backlogs to sudden, massive order cancellations. It is a deeply ingrained, high-stakes boom and bust cycle.
It really is a zero margin for error game, both in the quantum physics happening inside the machines and in the financial realities of the market. Let's bring this all together.
Sounds good.
We started this deep dive looking for the picks and shovels of the AI revolution, and we found ASML holding the exclusive keys to the 2-nanometer kingdom with their $400 million tin vaporizing EUV lasers.
We examined Lam Research using plasma to drill high-speed microscopic elevator shafts to solve the memory data bottleneck, and Applied Materials engineering the fundamental materials that serve as the foundational concrete for every single factory built globally.
We brought in KLA Corporation, acting as the ultimate quality control defect catchers in a microscopic world where a single speck of dust costs millions. And we mapped out how challengers like Canon are strategically trying to carve out memory niches with nano imprint stamps to save costs, while ETFs like SMH and SOXX offer investors different ways to bundle this whole wild ride together.
It is a staggeringly complex, ruthlessly competitive, and largely hidden ecosystem that physically powers literally every digital interaction we have in the modern age.
So the next time you hear about a revolutionary new AI model that can generate cinematic video, or you're just holding a brand new smart device in your hand, you now know exactly what is behind the curtain.
You're not just looking at a screen anymore.
Exactly. You are no longer just looking at the software interface. You know about the massive hidden picks and shovels machinery that physically built its brain.
You understand the incredibly fragile, physics-defying infrastructure making the modern economy possible.
But I want to leave you with a paradox to ponder. We talked extensively about how the entire goal of these massive equipment buildouts is to solve all the hardware bottlenecks for artificial intelligence, to make the processors infinitely faster and the memory instantly accessible.
Right.
But if these equipment manufacturers are too successful, if they manage to perfectly outfit the entire world with this ultra-fast, highly efficient AI infrastructure, what happens to their multi-million-dollar order books once the world finally has enough shovels? By executing their technological mission flawlessly, do they effectively build themselves out of a boom cycle? Do they engineer their own gold rush to an end?
ANM, American Northwest Magazine. Please subscribe. Thank you for watching.